Okay, welcome back. Third lecture of theory. Please.
Thank you very much. Thanks for coming back. So far, I gave on the results without any proof. So today, I will start trying to prove a little bit what I claim. So let me just recall what we did to Blackboard. We consider always a simple model, which is vorticity equation, including a given external field. And I convinced you that it's a good idea to start with the Cauchy problem being with the initial vorticity being a point vortex, so a Dirac mass located at zero and with intensity gamma. I report also some parameters that I will use which are used in the statement of the result that I will use today. The inverse Reynolds number, mu over gamma, which will be small, the aspect ratio, which is the size of the vortex core divided by some effective size, small, and some characteristic time and effective size. In the result I stated last time, yesterday, at the end of the lecture, was the following one. So you fix gamma, you fix Z0, so the initial data are fixed, one and the whole. The external velocity is also given, fixed, okay? Then there exists constants such that if the Reynolds number is sufficiently large, so the mu over gamma is sufficiently small, the unique solution, I claim that there is a unique solution to that equation, which I didn't justify, but this is a fact. The unique solution of this equation with this initial data can be approximated by some approximate solution. Probably I didn't write down again the formula for omega up, but we shall see it appear in the proof, of course. So omega minus some approximation, the leading order of which is the Lambert vortex, is controlled by it's small because it's controlled by epsilon cube plus delta epsilon square, so typically epsilon cube. Provided this is located at a moving point which follows more or less the dynamics of the external velocity field with an additional correction which is due to finite side effects, viscous effects, or whatever you want to qualify. So I will rediscover this statement, but I will let it here. And now we try to do the proof. So the proof is in 5 steps. Step 1, the most important one, you have to go to introduce self-similar variables. So this is the most important idea here, because you start with very singular initial data. So initially your solution will be very well concentrated. You don't see anything. If you still measure your unit of length is a centimeter and you don't adapt it to the size of the vortex, you are not in good shape. So what we do is we do the standard change of variables. So we look for solution of the form omega of xt to be gamma over mu t times some new function capital omega. So we move to capital letters of the self-similar variable, which depends on x minus z of t divided by square root of t, and which also depend on time. This is the ansatz for the self-similar solution. Very often done for the heat equation, and the same here for the vorticity equation. If you take the Biot-Savart of this, you obtain the corresponding relation for the velocity field, which I will write, although it's redundant, it contains exactly the same information. So for the velocity field, if you do the self-similar ansatz, it's gamma over square root of mu t times capital U of x minus z of t over square root of mu t, and so I will write both of them, but in fact I will only consider the first one. And so what do we know? So I will denote by psi the self-similar variable x minus z of t divided by square root of mu t. So the idea of introducing this variable is that this new coordinate, which will be my space variable, will be psi, plus x, we went to psi. Now the origin of the coordinates is z of t, the position of the vortex. I don't know where it is, by the way, but it will be solution of some ODE, but for the moment it's a 3-parameter. So where the vortex is, I center my coordinates. And now the unit length is no longer a fixed unit length, it's square root of mu t. So for small time, I measure in very small units, and in larger time, I adapt to the vortex. So this will make the initial data non-singular for the problem in the self-similar variable. We always see a Gaussian for small time instead of seeing a Dirac mass, and this is of course a big progress. Also, a remark that I can make, which is very simple, is that the circulation gamma here is the integral of omega of xt dx. This is how it was defined. So if you translate this, this implies that the integral of R2 of capital omega psi t with psi, this is always equal to 1. So in my similar variable, the vorticity profile is normalized to have integral equal to 1. The circulation gamma is taken out as a parameter. Okay. So now I have to plug into the evolution equation, and we obtain the evolution equation. Okay, evolution equation for capital omega. So evolution equation. So this is of course very important. So it's following from p dt omega of psi t plus 1 over delta times capital mu of psi t plus some quantity e of psi t, which I shall define shortly, dot grad omega of psi t is equal to some operator split L acting of omega of psi. So this is now the new evolution equation, which will be considered in the proof. Okay. And I will carefully explain all the terms. Okay, so let's try to study this equation. What do we see? So first of all, the time derivative becomes t dt. Everything now is dimensionless. All quantities I write is capital omega, the capital U are all dimensionless. So I cannot have dt. dt is 1 over time. T dt is dimensionless. So we can check that it's correct. I will comment on this t dt, but this is what replaces the time derivative. Okay. What is U? U, capital U, is just above of capital omega. And I do this change the variable, this is done in a scaling variant way. The Biot-Savart law is completely unchanged. It doesn't get in time, factor in time or whatever. It's still the same operation. Okay? So this is very convenient, of course. What is E? What is L? I should have begin with this one. What is this guy? L is the diffusion operator when you consider it in self-similar variable. So it's a diffusion plus some dilation, and this becomes a very important operator, Laplacian plus 1/2 side of gradient plus 1. This is a rescale diffusion operator, very familiar. Each time you do self-similar variables in parabolic equation, you end up with this operator here popping out, maybe with some. So all derivatives are with respect to psi. Now, psi is my space variable without any explicit mention, and when I differentiate the Laplacian, the Bayesian is all with respect to psi. So the Laplacian has been replaced by this a little bit more complicated operator. So it's a Laplacian plus diffusion, generator of dilation plus a constant. And now what is P of xt, P or P of psi t? This is essentially the effect of the external field. So E for exterior or external field. And let me try to write the expression in the simplest possible way. So if I write 1 over delta times E, which is what I have here in the equation, this is in fact square root of T over mu times F of 0 T plus square root of mu T psi T minus d prime of T. So it contains all the influence of the external field and also the fact that, of course, since I move to a frame with a different origin, I have the speed of this frame, which occurs in the equation, of course. And this I put together with the external field because there will be some cancellations. I will choose the z prime of t, so I have to partially cancel this one, so it's natural to keep these two terms together. So it's not more complicated than that. Maybe I can just write the external field in a slightly different form. So I have a remark. So what is delta times square root of t divided by square root of mu? There's some stupid algebra based on the definition I have written here. So you multiply both sides, both on top and bottom, by square root of mu. So it is delta square root of mu t divided by mu. But delta over mu by definition is 1 over gamma. So it's square root of mu divided by gamma. And now you multiply on top and on the bottom by T0. And then you obtain that this is gamma times T0. This is what is called V square. So it's square root of mu T divided by V square times capital T0. But square root of mu T divided by V is what I call epsilon. So finally, it's epsilon times T0 divided by V. It's natural, yes. Okay. Yes. T0 divided by V is 1 over speed, so let's make this dimension making. So if I go back to some I can write my E of phi D in a slightly different form, epsilon T0 divided by V, exactly the factor that I have here, times F of Z of T plus, and the square root of mu T that I have here, I can write that epsilon T times epsilon times psi T minus, well, sorry, this depends also on T, yes, minus T times, okay. This is just a new formulation. So you see that this term begins with an epsilon, I have an epsilon in form, and in fact, by choosing Z appropriately, it will start with epsilon squared. It's a small quantity in this series. Okay, now comes the most important remark about this equation. The Cauchy problem for this equation is imposed at initial time. This is not a Cauchy problem, because I have t dt. So if I solve that t is equal to 0, I have a big problem. Okay? But this is natural. I mean, I cannot impose the initial data at time 0 because they are forced to be the Gaussian, which is the profile of the self-similar solution, which is the fundamental solution of the heat equation. I cannot solve with any other initial data but a Gaussian. Okay? So this is a remark. I make more formal here. You can see that the setting t is equal to 0 in the equation for omega, which I write in ahead, we obtain, we get. So what do we obtain is to say brutally you put t is equal to 0 in this equation. So t dt becomes 0. Okay, assume everything is okay. So then you obtain 1 over delta times u dot r omega. This is the term with u. The term is e is gone because if I set t is equal to 0, epsilon is 0, epsilon vanishes at initial time. So the e has an epsilon in front, 0. Then with the right hand side, we obtain L times omega. So this is this equation. This equation is well known. This is the equation for the profile of a self-similar solution of the Navier-Stokes equation with circulation gamma and viscosity nu. Okay? If I look for a self-similar solution, I do exactly this ansatz, except that I have no time dependence. So I don't have the TDT. I have, of course, no external field. You don't change the two coordinates. Z of t is just 0, and so on. So you obtain exactly this equation for the profile of the self-similar solution. But the self-similar solution of Navier-Stokes equation have been studied. And if the vorticity is integrable and the integral is equal to 1, there is a unique solution to that equation, which is omega 0. So unique solution normalized is omega is equal to omega 0, where I recall that omega 0 sine 1 over 4 pi e to the minus psi squared over 4, and the corresponding velocity field u0 outside. I already gave this formula. It's 1 over 2 pi psi orthogonal of psi square 1 minus e to the minus psi square over 4. And this is what is called the Lamb-Ozin bond. So the only initial data I can consider are those ones. I cannot do anything else, which is good for me because I don't want to choose. So now I know that I have to start from those initial data, and then maybe I can make sense of this equation. Okay. So this was step 1. Any question? Okay. Self-similar variable, you obtain a discrete equation. I will keep the theorem maybe, but I can erase this additional stuff. So, step 2. Construction of an approximate solution. Not completely clear at this stage why we need to control an approximate solution. Maybe we could see that knowing that the solution you look for is close to omega 0 at initial time could be enough. You could write omega is equal to omega 0 plus a reminder. If you want to prove the existence and the uniqueness of the solution at fixed viscosity and small time, this is enough. But in fact, for what I want to do, which is more ambitious, which is the vanishing viscosity limit for an interval of time, it's absolutely not sufficient to say that the vortex is close to the initial delta. Okay? You need to construct a much more accurate approximate solution before being able to control the equation for the rest. So you have to believe me at this point, we have to construct an approximate solution. And as you see, the main contribution here in this from the external field can be expanded as a power of epsilon. Okay, so I will construct an approximate solution as a power of epsilon. So the approximate solution will be the following one. I construct omega r of psi t. The leading order will be omega 0 of psi. Omega 0 of psi is, of course, at the same time the initial data, but also the leading order in my approximation. Okay, and then this will be a power series in epsilon, but for some reason it starts at epsilon squared. There is no term proportional to epsilon. So the next term will be epsilon squared omega cubed of psi t plus epsilon cubed omega 3 of psi t plus epsilon 4 omega 4 of psi t. And the profile omega 2, omega 3, omega 4 have to be determined. And then I stop. Of course, I could continue. I think you can guess how it continues. But for proving the theorem that is here, stopping at order 4 is enough. It's necessary and sufficient. I cannot stop before. And for the velocity field, it's the same. You are, so again, it's redundant because it is obtained from the Biot-Savart law. But let me try it anyway. I will have a U0 of psi. U0 of psi is the one that I written there. Plus there will be some epsilon squared U2 of psi t plus epsilon q3 of psi t plus epsilon 4 q4 of psi t. Okay, so this is the form of my approximate solution. The problem is to find omega 2, omega 3, and omega 3. Some comments. So comments about this expansion. So first, I did already say that I just Biot-Savart of omega I for all I. All these profiles are obtained just by the Biot-Savart law, which is linear. So I need only determine the vorticity profile. Now this is an expansion in epsilon. So epsilon, I recall that epsilon is square root of mu t divided by t. This will be a small parameter, but it's time dependent. So the time dependence is here in the profile, but also in epsilon. In particular, when I set epsilon to 0, then for instance t to 0, all this is 0, so the initial data should be mu 0 and omega 0. So this is the reason I take the initial data here, because I have no choice. Okay, there is another parameter which is delta, which is mu over gamma, the inverse Reynolds number, which is very small. Everything depends on delta, not omega 0 and 0, because they are explicitly given, but in fact, there is another parameter delta which I don't write. This should be a two-parameter expansion, in fact, but it is implicitly understood that omega 2, omega 3, and omega 4 are also functions of delta. They could be expanded as power series of delta, but I don't want to write something which is too complicated. The main parameter here is epsilon. In the physical literature, these extensions are made in several papers over the last 20, 30 years. And there is a complete confusion always between epsilon and delta. Okay, I think it's very interesting to separate them. They are both small when the viscosity is small. Okay, and for the problem we are trying to solve with the initial data, which is Dirac mass, I have the relation that epsilon square is delta of t capital T 0, which means that epsilon and delta are linked in my case, okay, for fixed time. But it's more, I think it's more appropriate to think as epsilon and delta it could be two small parameters, and that I'm going to make an extension which is valid for both epsilon and delta flow. Delta is equal to 0 and epsilon non-zero makes sense. This will be constructing interacting vortices for Euler. You can try to consider vortex pairs from the Euler equation. You will do exactly the same thing. Then epsilon will not be given by this formula. Epsilon will be your initial data. There will be some small epsilon. There will be no delta because there is no viscosity. We will do exactly the same approximate solution, but with epsilon fixed and delta is equal to 0. It's not compatible with this relation, but which is a reason for considering epsilon and delta as independent parameters. Okay, now, okay, so what I have to do now is to expand, but this is very easy. So omega is expanded, u is expanded, and in the equation for omega, which is where, which is over there, there is also the e that has been expanded. So this is the only quantity for which I have no expansion so far, so I should do it. Okay. So assume. So for the moment, well, I mean, the equation for the center z of t, z prime of t, could be discovered in the course of the approximation. But let me give you immediately what the result will be. And we'll assume that z prime of t is exactly this formula, which I write in the form f of t of t, plus epsilon square d square Laplacian f of t of t. So this is just to say that if I don't know what z is, I could for the speed z prime do an expansion like that, and also solve term by terms to see what I can put for the velocity. The velocity will be determined. It will be determined by the expansion. So this is the order 0, this is the order 2, and there is no higher order at my level of precision. Now, what about e of psi t? So it's given by this expression here. Here you make a Taylor expansion of f. So I assume that f is smooth. I can do a Taylor expansion. And you see that if z prime of t begins with f of z of t, there is a partial cancellation between this term and this term. So instead of starting at order epsilon, it starts at order epsilon square. So this is the reason my expansion will start at order epsilon square, because the external field are also an expansion which starts at epsilon square. So this will be epsilon square E2 by T plus epsilon cube E3 of psi T plus epsilon 4 E4 of psi T plus, of course, a reminder which is order epsilon to the pi to the fifth power, because okay, this is not a polynomial in epsilon. Okay. What is epsilon? What is E2? It is all explicit. This is obtained. So you make a Taylor expansion here. The zeroth order term is compensated by the choice of the velocity here. So we find that E2 of FRC is C0 times the first order differential of f at point z of t acting of psi. It is linear in psi because of the first order expansion. And this is exactly what you obtain for E2. Okay. What is E3? E3 psi t is T0t. Then you have 1/2 times the second order differential for f at z of t acting on side, so the corresponding quadratic form. And then I have this contribution here, which also make a contribution at this order, which is minus the fraction of f at 0. Okay. Why we add this term? Because this cancellation will have some useful property, okay, which I cannot explain now, but will be obvious later. Okay, so this additional term here will make some quantity here vanish, not the full term. This is quadratic in psi, and this does not depend on psi, so it cannot be any cancellation between them. But some moment will be 0, and this is useful. Okay, and now finally, E4 of psi b is equal to T0 t square over 6 times the third order differential of f at 0 t t times 5 and 0. So if you follow a little bit this calculation, we can just conclude that this is completely stupid. I'm doing just basic expansion of the various quantities. I have in my equation a term E of psi t, which can be expanded in epsilon. So I look for a solution which itself is expanded in epsilon. So I do the most stupid stuff. I mean, this is obviously what you have to do. Further. Okay. And now I plug into the equation and I see what I obtain. So this was okay. It's okay that I still have the equation here. So I could just tell you, okay, you plug into the equation and you equal the same powers of epsilon and you will find the equation. Okay, this is, let me just do the calculation for the lowest order to find the first non-trivial correction. Let's do it very simple. So I have my approximation, I have my expansion on E, I plug everything into, I substitute into this equation. So what is T dt omega r? Let's start with the time derivative. Okay. Omega r is given by this. The first piece here does not depend on t, so it is 0. Now I obtain epsilon squared t dt omega 2. A priori, I don't know, but omega 2 may depend on time. Now I have epsilon. Epsilon squared is nu t over d. So here I have to use the fact that t dt epsilon squared is equal to epsilon squared. Epsilon depends on t, so I have to impose some rules like that in my calculations. So this is u plus omega. Okay. So there is a little surprise, and everything else is at this order of epsilon. I compute only up to second order so that I can see what is the leading. Okay, what is L omega r? Okay. L omega r is L omega 0, but L omega 0 is 0. This is what I have discussed here. There is an omega 0, the solution of this equation, but in fact, both members are 0. This is 0, this is 0. Okay? So L omega 0 is in the kernel of L, and we'll see that it's the only function in the kernel of L. So for that, so what I get is epsilon squared L omega 2 plus order of epsilon 2. Everybody agree? So the first term is here. Okay. Now I have to compute the non-linear term, u dot grad omega. So let's compute u r dot grad omega r. So this is perturbation extension. U0 dot grad omega 0, 0, for the same reason as here. This is the advection of a radially symmetric vortex by a radially symmetric velocity field. This gives 0. Okay, so this again starts at epsilon squared. So you obtain epsilon squared times u0 dot grad omega 2 plus u2 dot grad omega 0. Okay, plus everything else is at least of order epsilon cube. Okay, just give this cost product like that. Then it would be epsilon 3, epsilon 4, and so on. Okay, and finally I have this. E dot grad omega r, and this E starts at the order epsilon square already, so it's just epsilon square E2 dot grad omega 0 plus order of epsilon Q. No pitfall, no subtlety, nothing. It's just you plug and you see what it is. But the equation we obtain is quite interesting, okay? So, replacing, so we obtain. So I replace all this in the equation. I multiply the equation by delta because I have delta everywhere. So I obtain delta times 1 minus L omega 2 plus lambda omega 2 is equal plus E2 dot grad omega 0 is equal to 0. Let me explain, there is something to explain. So this equation involves two differential operators. The first one is L, which I recall Laplacian plus 1/2 size of grad 1. And the other operator is this capital lambda. Lambda is a non-local operator, which is what you obtain by linearizing Euler equation at the Gaussian vortex. Okay, we are very close to the Gaussian vortex, this Gaussian profile. The non-linearity is quadratic. When you linearize this quadratic non-linearity, you obtain a linear operator. So lambda acting on some vorticity omega is given by u0 dot grad omega plus Yosavar of omega dot grad omega 0. This is the definition of this operator. It comes from here. U0 dot grad omega 2 plus U2 from grad omega 0. This is what I write now, lambda omega 2. So this operator should not be, the first part is just an advection operator. You advect omega, capital omega, by the velocity field of the vortex. I mean, this is very intuitive. You have a radially symmetric vortex. The trajectories are running into circles. You put a perturbation on it, perturbation of the vorticity. What happens? One effect is that the perturbation is advected by the streamlines, okay? So this gives this local term, U0 dot grad omega. But there is another effect, is that the perturbation, which is non-radially symmetric, creates a modification of the vector field, which is non-radially symmetric, and will advect non-trivially the vortex. And this is this one. You compute the velocity field of the perturbation, and you act on it on the background vortex. So there are two terms when you linearize a quadratic non-linearity. You get two terms, and they have physically different effects. Yes.
Sorry, my ignorance. Is this something related to the magnet's effect or?
No. It's completely different. Okay. Okay, so I have a linear elliptic equation to solve with this diffusion operator multiplied by the small parameter delta, this integral differential equation. So this is just of order 1 differential operator, and this is of order -1. You take a primitive of omega and you act on a smooth function, plus E2. E2 E2 is given by an explicit formula and things like that. So this is a very nice function, which is completely explicit. And we have to see whether I can find omega 2, which is a solution of this equation. And at higher orders, you get equation of similar type. I mean, you obtain always the same kind of equation here. And you get more complicated terms involving higher order expansion and also the quantity you have computed so far. Okay. Now comes the most abstract part, is how do you invert this operator? So step 3. Let me call this functional framework. It's not obvious a priori that you can solve this equation, but it becomes much clearer if you introduce the nice function space. I didn't introduce any function space so far. And if you consider this equation, there is a very nice function space, which is a Hilbert space, a weighted L2 space with some Gaussian weight, in which both operator n and lambda have a remarkable property. So I define capital Y to be the space of all omega in L2 of R2, such that the integral of R2 of omega of psi square e to the psi square over 4 d psi. This is finite. So it's a weight into space with a weight which grows exponentially at infinity, which means that the elements in this space have a Gaussian decay at infinity in the L2 cells. They should decay roughly at least like e to the minus psi square over 8. So for instance, omega 0, which decays like e to the minus psi square over 4, is largely and comfortably in this space. Okay? But nevertheless, all elements have a Gaussian decay, and this is a Hilbert space with a natural scalar product. Okay. And now there are some results which are well known, which have been established a long time ago, at least 20 years ago, about the properties of the operator L and lambda in this function space. So I don't do a course in operator theory, so I should define the domain of the operator and blah blah blah. But let me skip that. All operators are defined on the maximal domain. Okay, and you have proposition 1, which tells you that the operator L, so the diffusion one, is self-adjoint in Y with discrete spectrum the spectrum is completely known and will not come to a surprise with you. Sigma of L, of course, in the space Y, it's just all the negative half integer. 0, minus 1 half, minus 1, minus 3 half, and so on and so forth. Very simple. And the Laplacian has continuous spectrum, the negative half axis typically. This one has discrete spectrum. And moreover, we know everything about the eigenvalues and the eigenfunctions. So the kernel of L, is spanned by, let me write this like that, by the function omega 0. One, the eigenvalue 0 is one, the multiplicity 1, and we know that the only function in the kernel is omega 0. Kernel of 1/2 plus L, so this is defined by two functions which are b1 omega 0 and b2 omega 0. These are the Hermite function of order 1. Okay? And so on and so forth. All the eigenvalues, the eigenfunctions are the Hermite function. This looks like an operator which is familiar to everybody, which is the quantum harmonic oscillator. This looks like that. The reason is that this is exactly the same operator. So, this is the statement, okay? And proof, well, if we are considering an operator in a weighted space, maybe a good idea is to conjugate with the square root of the weight to be back to the operator in L2, so that we can see what this operator is doing. So we do the calculation that E over psi squared over A times L times e to the minus psi squared of A, just conjugating the square root of the weight, and this is Laplacian minus 1/16 psi squared plus 1/2, and this is a harmonic oscillator. End of the proof. All the properties are just standard properties of the harmonic oscillator. So this, in case you have never seen this calculation, this is something very strange. You forget about all the Navier-Stokes equation. You start from the heat equation. We have an explicit solution, which is convolution with the Gaussian. You make self-similar variable. You end up with an operation where with an equation where the generator of the evolution is no longer the Laplacian, but this operator. Of course, you know an explicit solution because we can obtain it by the change of variable. So the semigroup generated by this operator, by the harmonic oscillator, is basically up to a change of variable the same as the semigroup of the heat equation. And this solution formula is called Mailer's formula in quantum mechanics and in many other books. So this is the simplest way of justifying is just to make this change of variable between the heat equation and this. Okay, so this is well known, and you see now why we choose this space here. It's the space in which the operator L is self-adjoint. basically unique. Okay. So this is good, but this is not all. The miracle is that lambda is already nice in the same space. In the same space where L is nice, lambda is also very nice, which has no reason, but is a fact. Okay. You can see why this should be true, but is it known? So proposition 2, lambda is skew adjoint in Y with the kernel of lambda being y0 direct sum plus the space spanned by the first order Hermite function. So they write the b1, b1, and get 0 plus b beta 2, b2, and get 0 with beta 2 in R. And y0 is the subspace of all radially symmetric functions. Okay. So this is the subspace of radially symmetric elements of Y. So the most important observation is that it is skew symmetric, it's skew adjoint, in fact. So it's very nice structure. I mean, you have self-adjoint plus skew adjoint. Okay, this is the structure of the linearized operator at the Lambda-Rosen vortex, which I studied with Jim Ring 20 years ago. And most of the results we obtain are based on this observation that lambda L is self-adjoint and lambda is skew adjoint. This has a lot of consequences. I mean, suppose that I look at the operator here. I have an operator of the form delta times 1 minus L plus lambda. This is the operator I have to invert. Okay. Now I know that this operator is always invertible. Why? Because what is the spectrum of delta times 1 minus L? Well, it's discrete eigenvalues. They begin at delta, right? So this is the spectrum of this delta 1 minus L. There are infinitely many, sorry, so I will stop at some point. But this is the spectrum. Now you have a skew symmetric perturbation. Eigenvalues can move only to the right. Okay? They become complex, but they cannot move to the left. So you never have any hyperdynamic instability. It's impossible when the generator is symmetrical skew adjoint, self-adjoint to skew adjoint. Just impossible. So the simple argument saying noticing that L is self-adjoint in the same space lambda is skew adjoint explains why all these vortices are so stable. There cannot be any bifurcations. You cannot have any eigenvalue crossing the imaginary axis. You know that the spectrum will stay in the same field. So this is very important, and this has been a little bit overlooked in the physical literature. Of course, people know that, but they don't observe that there are some consequences of it. So let's go back to our equation. We have to invert this operator here, on some function. The function in the right-hand side, e to the grad omega 0, is in my function space y, easily. So there is a unique solution. But this is not what we want, because there is a big problem. This degenerates as delta goes to 0. I mean, I want to have a solution to this equation, but this solution should have a regular expansion in powers of delta. Should not begin like 1 over delta. If you make a root short estimate here, you see that the norm of the inverse of this operator, so this operator is invertible. And if you take an estimate of the inverse of this, an operator from y to y, you see that it's certainly less than a constant over delta. But this is not what we want. 1 over delta is not good because delta goes to 0. Okay, so I need to have a regular expansion, and this becomes more difficult because if I want to have a regular extension, what does it mean? Okay, I have to erase something. Here, let me complete here. I want to prove that the solution of this equation is regular as delta goes to 0, I should be able to put delta is equal to 0 into the equation, and I have to consider the first the case where delta is 0. And then maybe I can start a perturbative expression. So the case where delta is equal to 0. Okay. Let me try to solve lambda times, it's not omega 2, it's just omega 2 evaluated at delta is equal to 0. So let me call it omega 2 bar, lambda plus E2, the grad omega 0 to be 0. And the question is, can I invert lambda? I know that I can invert this operator, but can I invert lambda? This is far from obvious because I know that lambda has a huge kernel, and I remind you that the orthogonal of the kernel of lambda is the range of lambda, the closure of the range of lambda. So if I want to solve this equation, I need this to be in the range of lambda. So at least a necessary condition is that it should be orthogonal to the kernel of lambda. This is a solvability condition. And there is an infinite number of solvability conditions because this means that this function here should be orthogonal to all radially symmetric functions in Y and also to these two ones, which are non-radially symmetric. So I have infinitely many solvability conditions to fulfill if I want to invert this operator. But the conditions are fulfilled. So let me write omega E2 dot grad omega 0, what it is. So grad omega 0 is minus psi over 2 times omega 0. So it's minus 1 half E2 dot psi times omega 0. And what is E2? Do I still have E2? No. So I lost E2. So E2, I remember, I still have it? No, I erased it. So it was first order derivative of f acting on psi. So if I take the scalar model of this psi, this is something which is quadratic in psi with the first order derivative as coefficient. So we find that it is minus E0 of 2 psi square omega 0 of psi, and then A of t cos 2 theta plus B of t sine 2 theta. It is just a direct calculation where this A of t and B of t, I already presented them to you, with 1 half B1 F1 minus B2 F2 evaluated at B of t. P and the B of t, I already wrote this formula, but there are more on the background. It's 1 half B1 F2 plus B2 F1 evaluated again and C of t and t. This is how the first order derivative of f enter the picture. So this is, and r and theta are now just the polar coordinates for psi. So in polar coordinates, it is r squared times omega 0 of r times a combination of cos 2 theta and sine 2 theta. Okay. So I know exactly what they are. Okay. Now, if I take the scalar product of this with something radially symmetric, this gives 0 because of the cos 2 theta and sine 2 theta. Only radially symmetric functions can be can have if you have no trivial dependence on theta, this is 0 when I take the scalar product with a radially symmetric function. So I'm orthogonal to this. Now, if I compute this first order derivative, they depend on theta, but only like sine theta or cos theta, not 2 theta. So again, I'm orthogonal to this phase switch. So my solvability conditions are satisfied. I am in the closure of the range of lambda, but I have much decay at infinity, so I'm in the range of lambda in fact. So there exists a unique solution to this equation. So we can prove that there exists a unique solution omega bar, which is in orthogonal to the kernel of lambda, such that lambda omega 2 bar is equal to plus E2 dot grad omega 0 is equal to 0. So I can at least solve the equation so omega is equal to 0. Okay. Now you are saying, oh, this is very abstract and so on. Can you give me a formula for this omega 2 bar? Yes, of course you can, because you plug into You know that the right-hand side depends on cos 2 theta and sin 2 theta. Everything is a rotation invariant. So the solution you look for, the omega 2 bar, also depends on cos 2 theta and sin 2 theta. So it remains to determine just the radial profile. You plug into the equation, you obtain an ordinary differential equation that you can solve. So let me write the formulas to convince you that this is nothing. Okay, so by direct calculation, just plugging and solving all the e's, we find omega 2 bar. So instead of saying that there is a unique one, I can give you the formula, you can just check that it solves the equation. Omega 2 bar of psi and G is P0 times some W2 of R, which is modulus of psi, times, let me just check that I'm correct, times A of T sine 2 theta plus, no, minus B of T cos 2 theta. It is, okay, this is the formula. So this is already known. P0 is a constant, so I have to tell you what this W2 is, okay? Where? Okay. So W2 of R is the function defined by H of R times phi 2 of R plus R squared over 2. Okay, now I have two new functions to define. So H of R, fortunately, is explicit. It's R squared over 4 divided by e to the R squared over 4 minus 1. An excellent function, okay? And phi 2 of R is the unique solution. It's in fact a string function associated to W2. It's the unique solution of the differential equation minus phi 2 second minus 1R phi 2 prime plus 4 over R squared minus 8 phi 2 is equal to R squared over 2 H of R. And this is the unique solution, so such that phi 2 of R is order of R squared and R goes to 0, and phi 2 of R is equal to order of R to the minus 2 as R goes to infinity. Okay? So this equation has a unique solution. You solve it, you plug it in, you obtain some W2, and maybe I can put the graph of W2. After all, maybe it's sufficient. It's something which is order of R squared near the origin, and which behaves like a Gaussian times a polynomial at infinity. And this is my function W. So W2 of R times this combination, completely explicit. This is the formula for the first order profile. So this is nothing mysterious. I mean, just plug into the definition. I don't do this exercise on the blackboard because you have to recall what exactly the expression of this operator lambda is and so on, but it's also reduces to ODE. So this ODE, we should look at this 4 over R squared minus H is strictly positive. Okay? And therefore, you can apply the maximum principle to this. This is positive, the right-hand side, so the solution here is positive. So this is positive, everything is positive, the function W is positive. And I make this observation because when you want to see, this is the function that is responsible for the deformation of the streamlines into ellipses, which the picture I made. And you want to see where the axis of the ellipses is, you need to know that W2 is positive. Otherwise, okay. Now we okay, so sorry for this calculation, but it's non-trivial to invert the operator lambda, but this is we know exactly when it's possible. So this is just the beginning. I didn't solve my equation yet, but let me, I want to keep this equation, so let me write this. So I know how to invert lambda. Now I can do either, I mean, there different way. I can continue solving perturbatively in lambda. So I claim that there exists a unique, so this was the first step here. There exists a unique omega such that here. Now, for the same reason, there exists a unique omega tilde in the orthogonal of the kernel of lambda such that lambda omega tilde plus 1 minus L omega 2 bar, it's omega 2 tilde, omega 2 tilde, this is equal to 0. It's the same argument because omega 2 bar, when you apply 1 minus L, you can see that you are still orthogonal to, you are still in the range of lambda, and therefore you can again solve. And finally, you define omega 2 as being omega 2 bar plus delta omega 2 tilde. Okay? So if I plug this now into the equation, I obtain that if I take 1 minus delta times 1 minus L omega 2 plus lambda omega 2, it does not give exactly 0, but if you replace omega by this and you expand and use the definition of this, you see that this is delta square 1 minus L omega 2 tilde. So this is order of delta square, so it's not exactly 0, but it's very small as a function of delta, and this is much enough for what I do. So this is like, in that sense, if I do that, I solve this equation to second order in delta. For delta equal to 0 and delta linear in delta, I have the correct expression, and I have order of the same delta. Okay, so this is basically how this profile in my extension are determined. Okay, I solve elliptic equation at each step to determine them. So it will be either the same thing for E3, so for omega 3 and omega 4. Okay, let me just make a comment without writing anything because I get tired. When you solve for omega 3, the right-hand side that you have to consider depends on theta, not like here, but with sine theta cos theta and sine 3 theta cos 3 theta. So the 3 theta doesn't face a problem with the orthogonality condition. But theta are orthogonal to this one, but not to this one. So you have to add some counter term, and this is the origin of the modification I can here with this Laplacian. It's to ensure the solvability condition to be orthogonal. These elements of the kernel are due to translation invariance, and therefore, by choosing the position of the vortex appropriately, I can always ensure that this orthogonality, if this one is satisfied. So at some point in the expansion, I have to add corrections to the velocity of the vortex, and this is to ensure this solvability condition. Okay, so you can check that putting exactly this Laplacian kills the component into this part of the kernel so that I can solve. Otherwise, I cannot solve the problem. The equation tells me you are not at the correct position. Yes?
So you want to solve omega 4? Yeah. Well,
no, for omega 4, it happens that you have sine 4 theta, sine 2 theta, and constants. In fact, there is no constants. So there is no, it's only at odd orders that we have to correct the equation in this effect. You can do all this algebra.
But it's interesting that this correction comes from just the numbers of the board. It's this calculation. Yet
No,
it's good for the omega 3, right?
yeah, because at the level when you write the equation for omega 3 is not more complicated. It's delta 3½ minus L omega 3 plus lambda omega 3 plus T3 the gradient omega 0 is equal to 0. You are right, it comes only at the moment there is only the level of the objects which is coming into the play.
I don't know if it makes sense as an observation, but let's say the correction that you have on the OD,
Yes.
this comes, let's say, just by plugging omega 0 in the equation for the center of this.
Yes.
So it does not rely on the expansion, but yet let's say this is useful.
Yeah, but what I'm trying to tell you is that if I replace the expansion just by omega 0, this term is unchanged. And if you look at the solvability condition at this, it depends only on omega 0 for the same reason. So the next correction to the position of the vortex, which will depend really on more, will be at order 5. That means when you solve the, probably, I didn't do the calculation, probably there is a non-trivial correction to add. And in that point, we will not be able to obtain it just by the ansatz or the vortex. It depends on omega 2, or I don't know, or I didn't do the calculation. Okay? Is it more or less okay? So there is an asymptotic expansion. It can be carried out in principle to any order. If you don't have the orthogonality condition, you change the C of T. The other orthogonality conditions are sort of satisfied by automatically, and you stop it at some order. And I claim that order 4 is sufficient for that purpose. Yes.
Right. I don't know if I understood well, but the equation in the block at the top.
Yes.
You want to solve it at order delta square.
Well, I mean, I'm happy with solving it at order delta square.
So I think in the second last equation, we need
If I do that, the terms which are proportional to delta are 0. These are just the terms which do not involve delta are 0. Oh yes, plus T2, sorry, plus T2 dot right omega 0. Sorry, this is all this which is equal to that. Sorry, this is a mistake. Get tired. So then the term of order delta is equal to the term which do not depend on delta are 0 because of this relation. The term linear to delta are 0 because of this relation, so it remains the term that are quadratic to delta. Sorry, of course, it's the full equation that we have. The box equation, the right hand side of the box equation becomes something which is delta square. Would be even better to have 0, but delta square is okay for me. Okay. Now let me summarize, and so this was the most technical or stupid part, say. So now let me summarize step 4, very easy step, what we have obtained. Okay. We have constructed, forget about this asymptotic expansion, so we have to construct it in some way, and this is not very important to know precisely how it was done. Okay? Just that it exists. So step 4, estimate on the remainder. Okay. So we have constructed the approximate solution. So we define the following quantity. R up is delta times T dt omega r minus L omega r plus not delta, so it's UR plus E dot grad omega r. So here I multiply the equation. I don't have anymore the equation for capital omega, but I put everything in the same member, everything to the left, and I multiply by delta, and this is the quantity which measures by how much my approximate solution fails to be an exact solution of the problem. If this was 0, you have an exact solution of the problem, but of course I don't have, so there is some remainder term which is measured by this quantity. So summarizing what we have done, we have proved the following thing, that with the construction we have, R of psi and t is bounded by a constant times epsilon 5 plus delta square epsilon square times 1 plus psi some power n times e to the minus psi square over. So this is for some constant and some integer. This is the remainder estimate that we have for the remainder. Okay, why do we have this? So all the terms we were working on have a Gaussian decay at infinity, so like a polynomial times e to the minus times 4 over 4, so this is this term here. And now we have epsilon 5, Why do we have epsilon 5? Well, because we computed the approximation up to epsilon 4. So the remainder start at epsilon 5. I could replace 5 by 7 or whatever by going to higher order extension. And delta square epsilon square here is just because we didn't solve the equation like in the box exactly, but only up to order delta square. So this was at the second order. So epsilon square times the delta square is here. But this reminder is small enough so that we can now study the equation for the exact solution. Is it okay? So this already the end of step 4. Very simple step. So now it remains only one step. What should I create? One. Okay. The final one. The final step of the course. I will have a little time to at least start with. Step 5. We call this energy estimate. So now I forget about the construction of this approximate solution, and I start again from the beginning, okay? I have an equation that I want to solve. This is this equation I call omega x, which was the equation for capital omega in self-similar variables. I build an approximate solution. Now I want to consider the exact solution. There is a unique solution to this equation, and I would like to show that it stays close to the approximate value. Okay? So we consider the exact. We make the following ansatz for the exact solution of my vorticity equation in self-similar variable with initial data, capital omega 0. Okay. So I have my exact solution, capital omega psi t. I want to write it as omega up of psi t plus delta times some correction, which I write w of psi t, which is unknown to me. So I write omega up plus a small correction, and for some reason I put a factor of delta in front of this correction. I will explain why. Okay. And as usual, I do the same for the velocity field. So u of psi t, and write it as u up of psi t plus delta times some v of psi t, and the small v is the dosara of w, of course. And this is the correction I have to add to my solution to obtain the exact solution. And what I would like to know is to show that the w and therefore the v stay small over some time interval. And then I will finish. We will have my approximate solution and the remainder. Okay. So is it difficult? Well, yes, a little bit, because let's look at the equation satisfied by this one. So equation for this is my last equation, the solution equation in this part. Equation for the correction. This is the correction to the approximate solution. And you will see much or it is very interesting to write this equation because it explains why we need all this construction. Okay. So this is t dt w plus, okay, let me write it in the following way. 1 over delta lambda w plus 1 over delta times some linear operator acting on w plus some quadratic form acting on w is equal to my diffusion operator L acting on w minus 1 over delta square times the remainder of the approximate solution. And I also observe that at time 0, I start from 0 initial delta. So this is my final equation I have to fight with W equation. Let me explain the A and the B rapidly, but this is nothing mysterious. We can find. Okay. Maybe here from colors could be useful. Okay, so B is just a nonlinearity, so B of W is just of W dot grad W. This is just a nonlinearity in the equation. It has not changed. Okay. Now we have more linear terms because we write a perturbation of omega r plus something. So A of W are the advection term, except for the part that has been written explicitly. Here I added and subtracting the same term. I made this term appear, but the same term will be subtracted in the definition of A. Just to have something cleaner. So A of W is UR minus U0 W plus B, which is BS of W, dot grad omega r minus omega 0 plus E of the psi T dot grad W. Okay, and here, this term here, and this term here all together make minus lambda, and this compensates exactly for this one. So this one is compensated by this one. I added and subtracted the same time. Yes.
Is there some one over that?
No, okay, very good question. This is what I wanted to explain. Yes, there should be 1 over delta in front of the nonlinearity, and this is a problem for me because 1 over delta in front of the nonlinearity I don't like. The only way I have to control this is to assume that everything is very small. So I decided to put this delta here. Okay, here or here, and then this gives the delta in front of the 1 over delta here. But this puts 1 over delta square in terms of the source term. Okay, so I have 1 over delta square in front of the source term, but I have nothing in front of the nonlinearity. So now, what do I have? I have an equation that I have to solve with 0 initial data. I like 0 initial data because there are nothing in initial data. Now, of course, if there is 0 is not a solution because you have the source term. The source term is whatever I have here divided by delta square. So this I have to divide by delta square. Okay? So delta square divided by delta square, good. It remains epsilon square, which is small. What about epsilon 5 divided by delta square? So epsilon 5 divided by delta square. Remember, epsilon square is delta times T over T0. So delta square is like epsilon 4. So this is epsilon times T over T0 square. It's order of epsilon. Okay. So even when I divide this by delta square, this remains small. And this is the reason why I have to go to order 5. To order 4 to have a remainder of order 5, so that when I divide by delta square, it remains small. Okay. If I just do a lower order expansion, it doesn't work out. Okay? So this is my explanation why I cannot prove theorem 1 directly. Your theorem 1 tells you that the trivial expansion, just omega r is equal to omega 0, should be even r. Well, but when you write the equation for the correction, this is horribly singular. At least the source term here, I can make it as small as I want at the price of taking an expansion to sufficiently high order, completely mechanical. So this whole extension has been done just to desingularize the source term. So now it's very good because I have 0 initial data, a small source term, an equation, so the nonlinearity will be okay as long as the solution stays small because it will be smaller. So I just have to show that the solution stays small. So this looks like an easy task, but there is a problem that I have this linear operator here, which are 1 over delta in factor, and delta goes to 0. So I just have to verify that this small quantity that has been injected by the source term are not amplified very rapidly by this linear operator. If I take brute force estimates on linear operators with 1 over delta, and we get a growth rate which is proportional to 1 over delta. So in a time proportional to delta or delta log delta, I will be just enormous. So I just now have to make energy estimates for which these terms are transparent.
And it's not technical, lambda square joints.
Yes. So for small time, it will be enough to we use the fact that lambda is still adjoint, so in that energy estimate, this term will be transparent, and this one is better. But for large time, it doesn't work. So this is the idea of the proof. I mean, it's completely classical. I mean, it's just, there is some preparation to write the correct quantities and things like that. We didn't find this immediately, but once you have the good tracks, it is absolutely classical. So the only thing that I have to do is now do energy estimate on this, because I just want to control the size or in some norm which contains the L1 norm, so it's not too much anything. Okay, so some energy estimate and take care that this term should not give too large contribution. Okay? So let me, well, I have a few minutes more. I will just explain how this can be done. Okay, I explained everything before. So let me try to do a simple case. Okay, this. I can write this here. For the blah blah. Okay, and here. So what I would like to do is for small times, which is capital P divided by T0 less than some numerical constant, it is possible to control the solution of WF on the time interval 0t using just energy estimates in the space Y, the space in which L is self-adjoint and Y is pure. So let me show you, maybe I will not have time to give all the details just now, but at least I can start. And if needed, we shall finish tomorrow. It will be very quick for me, it's not so difficult. So let's do an energy estimate. So for some consistency with the last lecture, let me define E of V, my energy will be just integral of R2 of W of psi square e to the psi square over 4 psi. By the way, it's just the norm of W y, okay? And the H1 version of this, which I will call F of W, which I will need, is the integral of R2 of e to the psi square over 4, say, psi square over 4, times gradient of W square plus psi square times W square plus W square inside. Basically, this is what will be produced by the linear diffusive part when you make the energy estimates, and which will help us controlling the various terms. Okay? So the energy estimate tells you that 1/2 PdT epsilon 1. So this E energy should not compute with the parameter, small parameter epsilon. Sorry, I will try to make it different. So this is the scalar product of W with PdT W. PdT W is given by the equation. So it gives what? It gives, as you have mentioned, okay, let me start with the diffusion term, W L W Y, this is the scalar product in Y. There is the term which has a lambda which is 0 because this one is skew symmetric, very important to know. Then you have 1 minus delta, 1 over delta, so this is a potentially dangerous term, A of W. Okay. Then you have nonlinearity minus W D of W W. Right? And finally, there is 1 minus delta square times W scalar product with the remaining term in 1. Very simple energy estimate. Okay? So let's look at the various terms and see whether they are difficult. They are not. In this case, just need to right? Then carefully. So here I'm using some well-known properties of these operators in the space Y, which I didn't before. So first of all, first remark that is extremely important, since the integral of W d psi is equal to 0, I forgot to make this remark, sorry. But omega r and capital omega have the same initial data, have the same integral. Integral of omega is 1, it was a normalization, and by construction, integral of omega r is 0, is 1 also, because omega 0 has integral 1, and all the other terms are 0 integral. So W has 0 integral. So since it belongs to y and has 0 integral, there exists some constant kappa such that if you take W L W in y, it is less than minus kappa times the functional which I call f. This produces minus Laplacian square, minus gradient square, minus psi square W square, minus W square. So this is very good. You produce all these negative terms just by the diffusion term. So this is of course very, very useful. And then let's look at the advection terms. By far, these are the diffusion terms. This was diffusion terms. Diffusion term. Diffusion term is good. It has a good sign. It produces negative quantities that will be useful. Good. Okay. Advection terms, of course, the most dangerous one are the one with 1 over delta. So, for instance, you have UR. So, for instance, you have integral. Let me denote to show you have a shortcut. P of psi is the weight, which is equal to the psi square of the. Okay. So I have to compute something like integral of P, and one of these terms here, whereas A is you have selected the form this term here. So you have integral of the weight times W times UR minus U0 dot graph W psi. How do you bound this? Okay, you can put the W here. So this is 1/2 integral of R2 of P UR minus U0 dot graph W squared. I can also move the gradient to put this as a divergence because it's divergence free. So I can write this as divergence of UR minus U0 times W squared. Then I integrate by parts and I obtain minus 1/2 integral of R2 of UR of W squared UR minus U0 dot gradient of P psi. Okay, so it's a velocity field, and the gradient of P, as I mentioned, is psi over 2 times P. So finally, it is minus 1/4 integral of R2 of W squared UR minus U0 dot psi multiplied by the weight P psi. Okay. And okay, so now UR minus U0, all this velocity field, I didn't mention that, but they decay like at least 1 over x at infinity, and the difference starts at epsilon squared. So in L infinity, this is order of epsilon squared. So from this, we obtain that this term here, and in fact, the whole term W A of W Y for the other term, no, it's completely wrong, sorry. The term I have computed, therefore, so this integral of R2 of P W UR minus U0 what is it dot W psi less than constant times epsilon square times W norm Y square. Very simple calculation. Now, I have epsilon square, I divide by delta. Epsilon square divided by delta is T over T0. So this can be normalized in the energy estimate. This is not a problem. Okay. So a term like that is okay. This one, okay. This one, similar calculation, even simpler, okay. This gives exactly the same bound. The difficult is the one which comes from the external field, and then we just try to mention this one, and then we are finished. So it's keep this theorem. A priori, it's good because you think it would be not too bad in the sense that the E2 here, the E starts by E2 and E2 has epsilon square in front. But it's not so easy because you obtain that the following thing. So we call that E2, E of psi t is epsilon square U2 of psi t plus order of epsilon cube. Everything epsilon cube is even better, so this will be okay. But E2 of psi t is bounded by a constant times 1 plus psi or something like that. You do the estimate. Okay. So it means that if you bound 1 over delta times W E epsilon square E2 dot gradient W, this will be bounded by something like 1 over delta integral over R2 of the way you will have W, you have the gradient of W, and then you have 1 plus psi. Okay. But okay, gradient of W you can put with P, it's not P squared. Okay, this can be norm of gradient. So you have exactly all the terms that are in this F here. So you can bound this by constant. So the constant is even 1 in that case. So it's epsilon square over delta, but now F of W. But this is E over T0. But F, I have only a finite quantity here in the right hand side, minus kappa. So if this is smaller than kappa over 2, this is good because this can be absorbed into the negative term produced by that. Otherwise, I am in great trouble. Because I cannot have nothing I can do. I mean, the gradient here and psi times W, it's exactly what you have in F. So I'm using all the power of the diffusive term to conclude. So this term is good only if you put some smallness assumption, and it can be pretty explicit. If you know this constant kappa, which can be computed, and then this is T over T0, so you obtain a bound. If you have this bound, it's okay, otherwise you are in trouble. And finally, the nonlinear term, okay? Okay, so nonlinear term. Okay, this can be bounded by f to the power 1/2 times e, and this will be small anyway in my argument. So let me just take for granted that this term will be okay. And the last one is trivial because it's 1 over delta square times W R in y, and this is bounded by constant, as I mentioned, epsilon 5 plus delta square epsilon square divided by delta square. So this is bounded by times W y. So this is bounded by C times epsilon times W in y. Then you can use your inequality, so you can give W square T and you obtain epsilon square, so this is okay. So you obtain a differential inequality for your energy, which is of the form, let me just write this. It is. So we obtain something like EET times my energy is less than, say, a constant T over P0 times this energy, plus terms that can be absorbed, plus this C times epsilon. So this tells you then you do a Gromval argument. You can divide by T, it's T dt, but this has a T, epsilon square has a T. So I can all divide by T, Gromval, and multiply by T after if I want. And then this obtains that on the whole interval 0 capital E, this energy here stays of order epsilon square. So the norm W, so this tells you that W of T in Y stays less than epsilon over the time interval 0T. This controls the L1 norm. W was the difference between omega and omega R. So you put everything in it and you obtain the statement of the theorem of gravity. Okay. And what is omega R here? This omega R here is just the version in the original variable of omega 0 plus epsilon square omega 2 bar. The only one that I can put explicitly, to put this is new omega R. Everything else is in the remainder. So this is very natural, except that this works only under a restrictive assumption on the time, whereas the theorem stated is for all time. So maybe tomorrow I'll start by explaining with the hands how you modify the argument in such a way that you can go any time. Going at a small time is a little bit problematic because I remember that I recall you that capital T0 is the time scale. For instance, if you have interacting vortices, it's the time for a rotation of one vortex around each other. I mean, the characteristic time on which you see an interesting dynamics for vortices. Of course, if you have to do only a fraction of this time, it's a little bit sad. Okay, your theorem is, but fortunately, we can do all the leapfrogging that we want or whatever. You can follow it to an arbitrary time, but this requires no trivial modification. So I will start tomorrow with explaining a little bit that. So now I finish more or less in the simple case. Sorry for
Thank you. It's funny lecture. Here, are there any questions?
yes.
Yes, so just a question for curiosity. Is it possible to do the same kind of results for compressive for equation?
Everything will change. Okay, so I don't know of any such result for compressive. There are a lot of things to clarify. This is representative for the rotational part of the compressible dynamics, but then you have the waves, or the wave part to deal, and this is completely different. So we are far from being, there are some little results in the compressible case, but we are more closer to just the one vortex and its stability or whatever. It's already the best we can do in the compressible case. I don't know if you have a comment.
I think there is one vortex in it gets more or less mean free condition. And a pair of vortices.
Yeah. So so I'm afraid this is not yet ready for, I mean, it's really incompressible stuff. This is when all the waves are gone and it remains only it's not excluded that if you start with a collection of vortices in the compressible case, the waves will go to infinity and the long time dynamics after some time will be governed by something which looks a little bit like that. But we are not able to prove that for the moment.
When we discussed before the spectra of liberators,
yes.
And the lambda, does that automatically imply or almost imply the stability?
Yes, yes. Yeah, when you look at the stability around the Lamb-Bosane vortex in self-similar variables, you obtain a perturbation equation, which is dW over dt is L minus 1 over delta lambda times W. Maybe with the assumptions that W as the open, okay? And then you know that this one is negative and this one is skew adjoint. It doesn't move the spectrum. So you have immediately an estimate which gives you exponential decay. This is not the original time. This is a very similar time which is logarithmic. So you get exponential decay in tau, which the algebraic decay in the original time. I will speak a little bit about that tomorrow because I will mention some results saying that you can do more using the enhanced dissipation effect due to this one. So it will be a little bit of that in my lecture too if I find time. But yes, the structure self-adjoint plus skew adjoint implies stability, but this is never written. For instance, the spectrum of this operator has been computed numerically with high precision in the 90s by students of Poulin in California and so on. There is even a PhD thesis on that. I read the PhD, they computed the matrices numerically. So you see when a matrix is skew symmetric or symmetric, it's never written in the thesis that they should know it. And then the implication to stability, which is completely obvious, is not even mentioned. So this is sort of folklore. You ask physicists, they say, oh yes, of course, this one, but the fact that you have exactly this prevents all hydrodynamic instabilities. If you look at the flow around, some unstable shear flows or whatever, such a condition is not true. So it is very specific, and this is why, and I should really emphasize, I should have more emphasized that all this, what we do here is based on the fact that at each step you use the information that one vortex is a very stable object. The faster to rotate, the more stable the vortex is, which is in contrast with flow past an obstacle or whatever. When you increase the Reynolds number, you trigger instabilities. Here, it's like the vortex is always stable by the argument you mentioned, but even there are quantitative statements saying that the faster the rotation, the more stable you are. So this is why we can do some vanishing viscosity limits with objects that are so singular, because we are helped a lot by the stability of the object. A point vortex is a very stable, a very simple object. It can only move. So a curve, like for vortex sheets, is more complicated. It can make complicated motion on the boundary of a vortex patch or whatever. A point vortex can only move, so it's a very simple object. And it's very stable, and that's the reason why we can control in a regime where we shouldn't be able to control the vanishing viscosity limit for in this limit, the velocity field is incredibly large near the vortex. So you have very high rotation, but for the reason you mentioned, this doesn't create any instability. Quite on the contrary.
Any other questions? It's quite clear that you can say all those things in a regime where weak solutions don't even make sense.
For Euler. Yeah, for Euler, yes. But in some way, we are indicating what should be viscosity solutions for Euler in that particular case. By taking that instance, yeah, it's sort of an accident due to the very specific and simple nature of the problem. The obstacle for Euler is very known, and we can avoid this. I don't say that it will always be the case. We cannot solve all problems in hydrodynamic stability in that way. It's a simple one.
Okay, so we thank Thierry again. And we see tomorrow night.